Yeah. Hello everyone. So today we are going to see about the gas turbine power plant. Okay, myself, Dr. Murugan, working as associate professor in the Department of Mechanical Engineering, Konku Engineering College. So today we are going to see about the gas turbine power plant problem. This is the question. In a gas turbine power plant, which works on a Brayton cycle, the inlet air temperature is 30 degrees Celsius and the pressure is 1 bar. And the pressure ratio is 6.25 and the maximum temperature of 827 degrees Celsius. So we have to find out the compressor work, turbine work, cycle efficiency, and the work ratio. Okay, so this is the thing we have to find out. So first, as I said in the previous videos, whenever a problem is given, we have to write the given data. First, we have to understand the questions and then we have to write the given data. So the initial temperature, that is the inlet air temperature, is 30 degrees Celsius, we have written here. And we have to write in Kelvin. So the 30, so 273 plus 30, it gives 303 Kelvin. And the pressure, initial pressure is 1 bar. That is, we have to convert it to kilopascal. That is 100 kilopascal. And the pressure ratio is 6.25. So the maximum temperature is 827 degrees Celsius. So in the Brayton cycle, which point we will be getting the maximum temperature is the third point. That is the third point we will be getting the maximum temperature. So we can write as T3, that is 827 degrees Celsius. And when converting into Kelvin, we have 1100 Kelvin. And whenever a problem, the gamma value is not given, we can assume it as 1.4. Okay. So we have to find out the compressor work, turbine work, cycle efficiency, and the work ratio. So first we have to find out the T2. So the initial temperature is given, the final temperature is given, the intermediate temperature is not given. So we have to find out by using this method. So we know that the T2 by T1 is equal to P2 by P1 or gamma minus 1 by gamma. So this T1 goes to the other right hand side. So the equation becomes P2 by P1 into gamma minus 1 by gamma into T1. So the T2, and what is P2 by P1? That is a 6.25. That is the pressure ratio. The pressure ratio. So we are substituting the term for RP as 6.25, and we are quoting all the data in this formula, and we obtain the final temperature T2, that is 511.5 Kelvin. And similarly, we need to find out the final temperature, that is the T4 temperature. So this T4 temperature can be found out by using the formula T4 by P3 into P3 by P4. P4 by P3 for gamma minus 1 by gamma. So what is P3? What is P4 by P3? It is the ratio, that is 1 by inverse of pressure ratio. So we have written as 1 divided by 6.25. Okay. So we obtain the final temperature is 651.63. So we have got all the temperature in this TS diagram. So the initial temperature T1 and the intermediate temperature is 511.25, and the third temperature is already given, that is 1100 Kelvin, and the final temperature is 651.6 Kelvin. And first we have to find out the compressor work. The compressor work can be calculated by using the formula, simple formula, that is the compressor work is mcp delta T. So m is, if the m is not given, that is the mass is not given, we can assume it as per kg. Okay, we can make the calculation for per kg. So mcp of delta T, cp value of air is 1.005 kilojoule per kg. Okay, and the T2 we obtain the temperature, and T1 the 303 Kelvin, and we find out the compressor work, that is 209.54 kilojoule per kg. And the turbine work can be calculated by using this formula. This is the compressor work from 1 to 2, and this is the turbine work. Okay, from this is the place where we obtain the turbine work. Turbine work, and this is the compressor work. And the turbine work is given by the formula Cp of T3 minus T4, that is 450.61 kilojoule. So the Brayton cycle efficiency is calculated by using the formula 1 minus 1 divided by Rp power gamma minus 1 by gamma. So what is Rp? That is 6.25, which can be written like this. That is 1 minus 1 divided by 6.25 1.76 percentage of efficiency for the Brayton cycle. And we have to find out the work ratio. What is the work ratio? That is the difference between the compressor turbine work and the compressor work divided by the turbine work. Okay, so we note that is the turbine work ratio is given by 0.5. So this is the typical Brayton cycle problem, and we can see the another problem on the gas turbine. That is, a gas turbine takes in air in at 15 degrees Celsius and 1.01 bar, and the pressure ratio is 6. The isentropic efficiencies of the compressor are and the turbine are 0.82 and 0.85 respectively. Calculate the power output in kilowatt of an electric generator geared to the turbine when the air enters the turbine at 600 degrees Celsius and the mass flow rate of air is 15 kilogram per second. Also calculate the overall efficiency of the plant. So we have to write the given data. 15 degrees Celsius plus 273 gives 288 Kelvin, and the pressure is 1.01 bar, that is equal to 101 kilopascal, and the pressure ratio is 6. So we can write it as Rp is equal to 6. What is pressure ratio? That is P2 by P1, that is the final pressure divided by the initial pressure. And the efficiency, isentropic efficiency of the compressor and the turbine are given, that is 0.82 and 0.85, and the temperature of the air enters into the turbine, that is 600 degrees Celsius plus 273, it gives 873 Kelvin with the mass flow rate of 15 kg per second. Similarly, like previous problem, we have to find out the temperature T2 and T4. So temperature T2 can be found out by using the relation, the T2 by T1 equal to P2 by P1 by gamma minus 1 by gamma. So we obtain the T2 480.53 Kelvin, and the compressor efficiency is calculated as T2. See here, T2 1 to 2 dash and 2 3 dash. It represents the isentropic efficiency. Okay, so we have to obtain the temperature of T2 dash as well as the T2. So we can write the relation, that is T2 minus T1 divided by T2 dash minus T1. We have found out they have given the isentropic efficiency of the compressor as 0.82. So the 0.82 is related with T2 minus T1 divided by T2 dash minus T1. So the T2 dash can be given as 522.79 Kelvin. Likewise, similarly, we have to find out the T4 temperature as well as the T4 dash temperature using the same relations what we obtained here. Okay, so the same relations we can obtain here as 575.69 Kelvin. And after finding out the T2 dash and T4 dash and T2 temperature and the T4 temperature, we can find out easily the compressor work. Now, the compressor work can be given by the formula MCP of T2 minus T1. That is MCP of MCP delta T. Here in the previous problem, the mass flow rate is not given. In this problem, they have given the mass flow rate, that is 15 kg per second. So we are implementing the data in the given problem. I have given formula, and we relate that 15 into 1.005 into T2 dash what we obtained previous, and minus T1, that is the compressor work is 3550.16 kilowatt, and the turbine work, that is the same problem, that is T3 minus T4 dash. So the turbine work is given by 4481.95 kilowatt. So the work net, our work output is actually, we know that the work developed by the turbine minus the work created by the compressor. So 931.79 kilowatt. So the heat supplied can be calculated where the heat is supplied, that is from the process. Here this is the heat addition process. Heat addition process, and the process 1 to 3 is the heat rejection process. Okay. Now we can find out the heat supplied, that is MCP T3 minus T2 dash, and we obtained over 970.5279.41 kilowatt. So finally we can obtain the data, that is finally we can obtain the data from this. So we can write, we have to find out the efficiency, that is 931.79 divided by 5279.41. The answer is 50.79 50.42 percentage efficiency. Okay, so today we have seen about the problems. If you are having any doubt, discuss with me.